molality, page 365, molality. Now we've had a couple different units of concentration we've dealt with so far. Specifically in here we've got molarity and molality. What is the abbreviation? What symbol are we using for molarity? Capital M. Big M, yep. That's the way they describe it in elementary school, big M. Here it's capital M. Molality, lowercase m, little m, lowercase m. Molality and molarity. It's important that you be able to differentiate between the two things. Okay. What are the units of molarity?
Is it moles?
Here, I'll put it right over here. For molarity is the number of moles of what? Solute per liters, or you can put the units here. The number of liters of solution. Okay? Molarity is moles of solute per liters of solution. Molality is what? The number of moles of solute. Solute? No, solute. Okay. Solute. Number of moles of solute per kilograms of solvent. Now, just something you're going to have to memorize, okay? But let's look at this for a moment and remember and notice a couple of things. First of all, for the molarity, moles of solute, liters of solution. This one pretty much makes sense. But notice, let's say if we're going to change the molarity of something, we have a solution, and we're going to change the molarity as I pour more in. Let's go back to salt water. We've got water and salt in that salt water. We've stirred it up. It has a certain volume, right? If I take additional salt and add more salt to that mixture, I've increased the number of moles of salt, but in doing that, I've also increased the volume of the solution. You get that? I've got a certain amount of liquid, I add solid to it, and I look at the level, how much solution I have, and as I add more salt, the volume will go up. It'll go up because I'm adding volume to it of the salt. So as I add solute, my solution volume goes up. Now, notice on molality, my moles of solute, the same exact thing. But if I have a beaker and I'm adding more salt to this salt water, as I'm adding more salt, does the denominator on this measure change?
If you add more what?
If I add more salt and I'm checking the molality, my number of moles of solute is going to go up, but is my number of kilograms of solvent going to change? No. Because solvent, remember, is the water. In the case of salt water, salt is the solute, water is the solvent, and the combination is the solution. It's a noisy corner back there today. So, up here, if I add salt, my molarity is going to increase, but my number of moles is going to increase, but so is my volume. Down here, my molality, the number of moles of solute is going to change, but the kilograms of solvent is not going to change. I would have to add salt water to increase the kilograms of solvent, right? I need to add water in some way in order for this denominator to go up, which means you're going to see a greater rise in the molality than you will in the molarity. Okay? Ultimately, it comes down to this of remembering the definitions. This is per liter of solution. This is per kilogram of solvent. In the saltwater analogy, this is what is the volume of the total that I have. This is how many kilograms of water do I have. It's not, that denominator is not going to change unless you add more solvent. I wrote this down in my notes. It says that molality is the ratio of moles of solute to the mass of the solvent. The mass of the solvent. This is the ratio of moles to the volume of the total solution. So molarity is volume, molality is mass. Now, why is that significant? Well, actually, let's go ahead and let's look at example 10.2 before we talk about the significance of molality. Example 10.2, it says a chemist mixes 3.4 moles of sodium chloride with 4.5 kilograms of water. There's our basic model to understand this concept, salt water. So we've got 3.4 moles of NaCl, 4.5 kilograms of H2O. What's the molality of the solution? Well, simply we're given moles of sodium chloride. If we're going the molality, we've put our 3.4 moles in the numerator and the 4.5 kilograms of water in the denominator, and that comes out to be 0.76 lowercase m molality. That's the molality of that mixture. Pretty straightforward. The second part of example 10.2, they give us a mass of zinc chloride, ZnCl2. So if you're given a mass, but you need moles, how are you going to get moles from the mass? If I'm given the mass and I need moles, think of a solution pathway, right? So you're coming down in our solution pathway, you're moving from mass to moles, you're coming down, and the information between there is the molar mass. So the mass divided by the molar mass is equal to the number of moles. So that'll give you the number of moles of zinc chloride divided by 150 grams of water. So that's 0.15 kilograms. And then it's just a division problem after that. Remember that the units are kilograms, not grams. That's another common mistake. Okay? So it's the number of moles in both of them. Moles of solute in both of them. Liters of the whole, mass of the solvent. In kilograms, not grams. All right. So on your own 10.6 says calculate the molality of the following solutions. Just what would the math look like? We've got 4.6 moles of sodium hydroxide dissolved in 2.4 kilograms of water. The molality is going to be, the numerator is 4.6, the denominator is 2.4. Do the math. B, it says 125 grams of potassium nitrate in 1.22 kilograms of water. Okay, what would the math look like here?
125 divided by the molar mass of K03 and then divide that by 1.2.
Okay, everybody get that? On B, it says we have 125.0 grams of potassium nitrate. Okay, so we're going to have to compute the molar mass of potassium nitrate, divide 125.0 grams by that molar mass to produce the result there being the number of moles, then dividing that by 1.22, which is the mass of the solvent in kilograms. Do that math and that'll be your molality. And C, 65.2 grams of lithium bromide dissolved in 750 grams of water. What's the hook here on C? What are they testing on C that they didn't test on B?
We have to figure out which is a solvent, which is a solute.
No. No.
They're both grams.
Okay, so what piece of information did we need to figure out 125? We needed to figure out the molar mass, right? So mass divided by the molar mass. In C, don't you need to figure out what the chemical formula for lithium bromide is? Because you can't figure out the molar mass of lithium bromide if you don't know the formula for lithium bromide. What would it be?
What's the charge is?
We've got lithium, which is a column 1, bromine, column 7. So it's a 1-to-1. LIBR. You've got lithium is a +1, bromide is a -1. The bromine ion, -1 bromide. So it's a 1-to-1. 1 lithium balances 1 bromine. Isn't that correct?
I mean, I was thinking, I guess so.
The same as sodium. See, sodium is in the same column as lithium, and chlorine is in the same column as bromine.
So do you just not count the column on the far right?
Yeah, those are the noble gases. They don't want to react with anybody.
That's where I got confused.
Okay. So column 8 is, column 8, the noble gases are like, leave us alone. We're not reacting with anybody. We don't need all the drama. Just leave us alone. Okay? This side of 8, see how many more elements are involved in drama? And these are the slow and steady, never get thrown off course, right? Don't fail a quiz because their best friend didn't say hi to them in the hall before class. I mean, they're fine. The noble gases, you just carry on. They're the introverts. Everybody else here, drama. Okay. Drama, that's what chemistry is. It's a drama between the elements. Okay. But in C, you need to know, be able to figure out, they give you lithium bromide, you've got to figure out what the chemical formula for lithium bromide is so that you can then figure out the molar mass of lithium bromide. So you can then divide the mass of lithium bromide by the molar mass of lithium bromide to get the moles of lithium bromide here, and divide that by the mass of the water in kilograms, which would be 0.75. 0.75 kilograms. 750 grams, right? So make sure you convert the denominator into kilograms. Use the unit as kilograms. All of that, computing molality, first of all, we need to be able to compute it, and then we're going to use it. And we're going to use it in both freezing point depression, which we'll cover today, and boiling point elevation, which is basically the same thing in reverse. So once we talk about freezing point depression, if we need more time on freezing point depression, we'll do that tomorrow. If you still don't get it, we'll ball that together with boiling point elevation. Okay, but I'm confident you can get this. It's pretty straightforward once you understand this formula after you hear the concept of freezing point depression. Starting on 367. We don't have time to do experiment 10.4 because experiment 10.4 is a long-term experiment. It's something that you have to, remember this book was designed for homeschoolers, so they set up the experiment, they put it in their freezer, they go on with their Latin or whatever else they have at home, and then they come back and they check the freezer every hour or so. We don't have time in class to do that. Okay, so you're going to have to trust me and trust the book on what happens. If you want to do it at home, that's fine. If you want to borrow a thermometer to do it, we'll loan you one, okay? But here, let's talk about this concept of freezing point depression and why there's such a thing as freezing point depression. Now, looking on page 368, this is what William and we're used to seeing when it comes to the winter. You see the salt truck there in that picture? No, they don't have these things down here, do they? In the same way, you guys don't use salt here in the south. Actually, in the mid. You guys don't use salt trucks like this. You guys use brine trucks. Looks more like something we would see on a farm. Drives down the road, and it's got that long hose in the back, and it's spraying water on the road. Strike you as odd that they're concerned about freezing temperatures, so they spray water on the roads? Now, when you understand the science behind it, it might make more sense. But just that concept of, it sounds counterintuitive, doesn't it? We're afraid the roads are going to freeze, so we're going to coat them with water. I'm afraid you're going to catch my germs, therefore I'm going to cough on you and wipe my hands all over you. Okay? But actually, if we take that analogy a little bit farther, I jokingly said in one class that one of the main reasons that people are getting so sick nowadays is because of hand sanitizer. Thank you. Because of it. We're getting sick because of hand sanitizer, not staying healthier because of hand sanitizer. Why would that be?
Everybody's touching it.
Yeah, everybody touches the bottle before they use it? No, that's not it. But this kills germs, doesn't it? So why would you get sicker if the germs are killed? Because we're decreasing your body's ability to fight germs. So if you lived in a perfectly sterile environment, you wouldn't need all the antibodies and everything working. So the more we deprive you of the opportunity to get micro-sick, the more we enable you to get seriously sick. What's a vaccine? When you go get a shot from the doctor, they give you a controllable case of whatever it is you're trying to prevent. Sounds counterintuitive, doesn't it? I'm going to give you a chickenpox virus because you don't want to get chickenpox. I'm going to give you a measles virus because I don't want you to catch measles.
Because it gets your body to get used to that.
Right, you build up an immunity to it, so your body can fight it. Hand sanitizer is the anti-vaccine, right? Let's make sure you live in a sterile environment. That way your body doesn't get antibodies. That way when somebody beside you is sick, you really get sick. Okay. All that has talking about counterintuitive. We make you micro sick so you can stay healthy. We kill micro germs so you can become incredibly ill. And here we spray water on roads to keep them from freezing. Now, if it's just water, that's one thing. And by the way, we've mentioned before that the water that comes out of the tap is not just water, is it? So water coming out of the tap, ladies and gentlemen, does not freeze at 32 degrees Celsius and 0 degrees, at 32 degrees Fahrenheit, 0 degrees Celsius. It freezes about there, but not exactly there, because it has stuff in it. It has solutes in it. Those solutes in it change the freezing point and the boiling point. Now, it'd have to be really loaded with solute for it to change in a major way. So it's going to be really close to 32 degrees. And so when we're talking water freezing at 0 degrees Celsius and boiling at 100 degrees Celsius, realize we're talking about distilled water. Water that has had all the solutes, or as much as we can, removed from it. Because the presence of a solute is going to change the boiling point and the freezing point. Okay, so when we talk about H2O, that's why that question we had on the practice problem that had the lead ions in the water, it didn't really register to us that the lead ions were in water. Not that the water, because the water has all these solutes in it. In that case, the lead ions were a solute in the water. They would have affected the freezing point and the boiling point. It will not be exactly at 0 and 30 and 100, 0 and 100, because there's a solute in it. And the way we compute how far off of 0 or 100 is going to be is using the molality. How many moles of that stuff is in a given solvent per kilogram? So when a brine truck goes by and it's spraying water on a road when it's near the freezing point, what it's spraying on the road is not pure water, it's salt water, it's brine. That salt in the water is lowering the freezing point of the water that's on the road. If there's water on the road already, or when the snow falls, snow is frozen water, right? When that frozen water comes in contact with, it either melts or comes in contact with the liquid water, it will become liquid, okay? And when it becomes liquid, it will pick up that salt that's in solution and bring it into the solution. And when that water on the road has salt in it, the freezing point is now lower than it was as pure water. Let's say hypothetically that we have one road that's sprayed with water and one road that's sprayed with salt water. On one of those roads, it's going to freeze at 32 approximately, and the other one, let's say it freezes at 28. What will happen if the ambient temperature is 28.5, 29, 29.5, 30, 30.5, 31, anywhere between 29 and 30 and 32 degrees Fahrenheit, okay? When the snow falls and melts, it will not freeze, even though it's below freezing. Now, there is a point where it's going to get cold enough that even though it has salt in it, it will freeze. Okay? So all we've done is taken the point where it freezes and now reduced it, which gives us maybe 4 or 5 degrees of temperature difference before it freezes. So salt water on the road, hypothetically, let's just say, the salt water on the road doesn't freeze until 28 degrees, which means the road won't become icy until the temperature outside goes below 28 degrees, whereas before it would have gone at 32 degrees Fahrenheit. If it freezes at 0 Celsius, now it might freeze at -3 or -4 Celsius. So you've got those 3 or 4 degrees where it's going to stay drivable. It's going to be liquid. Your concern there is hydroplaning, not sliding on the ice. Okay? That's the concept behind it. Now, why does this happen? They give an explanation of this on 368 as well. So here's what's happening. What's taking place inside the solution? And here again, I want to say, if we were on Miss Frizzle's school bus and we go down to the molecular level, what is it that we would see? Well, if we had pure water, pure H2O, in the liquid form, Okay, again, the hand demonstration. This is about the kinetic theory of matter. Freezing and boiling has to do with kinetics. And so we have H2O, H2O molecules. They're together and they're in liquid form. Solid form, they're vibrating. Gaseous form, they're bouncing off the walls. Okay? Liquid, they're staying pretty close together, but they're free to move around. Right? They're free to move around. What happens when liquid that's moving around like this, in order for it to freeze, what has to happen? Don't think in terms of temperature. What has to happen to the motion? This is liquid water. What does solid water look like? In kinetic, the molecules of water are going to vibrate, but they're not going to have motion relative to one another other than the vibration. Remember? Liquids, solids. So as we go from ice to liquid water to steam. Here, we're starting with a liquid, and we're trying to freeze it. When it freezes, what happens? The energy of motion has to be removed. And when the energy is removed, they come into alignment and they vibrate. So when something freezes, I don't want you to think of freezing as reducing the temperature. I want you to think of freezing as reducing the energy. And when you reduce the energy, when you pull the energy out of it, it moves from liquid, it moves from the molecules moving like this to the molecules only moving like this, which to us changes it from a liquid to a solid. It's not the temperature that does it, it's the removal of the energy from the molecules that does it. Okay? Now, we have water, we remove energy, which is decrease the temperature, it draws the energy out of it, because it's going for equilibrium, right? If we put something warm in a cold place, the energy is going to get sucked out of the warm thing into the space. It's going to heat up the room around us. It's going to heat the surrounding and cool itself. So the water is in motion, and as it loses energy, it starts getting sluggish. As it gets cooler and cooler, because we're removing more and more energy, then eventually they lock into place and just start vibrating. If we have water, and we add a solute into it, what is the nature of dissolving? When we add a solute to a solvent and it dissolves, what is happening? The molecules of the solvent are coming in between. They have energy because of forces of attraction, right? They're attracted into the solute. They're separating out the solute. If it's a covalent solute, it's separating it out in individual molecules. If it is an ionic solute, it's breaking it down into individual ions. The whole process of dissolving has to do with opposite charges, attraction and repelling, right? Those natural charges, those charges which result in attracting and repelling, cause motion. They move, which is why when you dissolve something, energy goes in to the solution. When you dissolve a solute, it is generally an endothermic, it's an endothermic reaction. The water cools because inside it's warming up. There's more motion taking place. So, you have water in motion. You add a solute to it. What happens? It speeds up. It speeds up. Why? Because now you've got molecules chasing molecules. Before, they were free to move. Now, they're on the hunt. They're moving more. So adding a solute to a solvent causes the molecules of the solvent to move more, because now they're in a feeding frenzy. Way to think of it. Piranha, you drop the carcass of beef in there, the beef is the solute, the piranhas are the solvent. Guess what? They were just swimming around looking for food, but now they're in a feeding frenzy, and the water's churning. Okay? That energy that you've just given them means you got to take more energy out before it's going to stop moving. And because you got to take more energy out, motion stops at a colder temperature than it normally would, because you have to take more energy out, which is why the freezing point is lower than it would be. have a bunch of, have a couple kids over here and a couple kids over here in the gymnasium and make them sit in chairs and not move, okay? And then say, okay, there's a couple of balls, go. And they take off, right? And they start working, they're moving around. Why? They want to play. They, you know, and I know that molecules and atoms, they don't have these desires like we have, but let's think of it that way. These kids are molecules. They were in a certain position, they were fidgeting in their seats, they're able to move around, but now you say, okay, game on. Poof. Suddenly they're playing, they're getting sweaty, they're pushing each other, all this, you know. I'm working on media analogies, but I'm not going to go there. So now they've got this opportunity to go out and play. All this energy is taking place. Now, when they're sitting in their seats, not able to mix, and they start to misbehave, how do you just say, hey, quiet down. Hey, you know, it's easy to control them that way. But when you're out there playing the game, and the period's about to end, how do you stop it? You might have to blow a whistle. You have to do more to stop it, because now they're in the chase. Now they're in the game. It takes more to stop it. More to stop it, when we're talking about kinetics, is taking more energy out. Taking more energy out means, the way we understand it, is to cool it, to bring the temperature down farther than you normally would have to. Okay, but it's the motion between the molecules or ions created by the attraction and repulsion of charges that add energy to the mixture, which we need to overcome by taking more energy out, which is a lower temperature. Okay. My outline went something like this. Liquids are in motion. Changing to a solid phase requires a decrease in motion. Okay? So they're moving around, but to become solid, you've got to slow them down and stop them. So they're in motion, we need to decrease the motion. And to slow them down means you need to take the energy out of them. For little kids, we let them start playing and tell them they can't stop for 4 hours. Okay? At some point in the middle, they're going to be like, can we just take a break? Like, no, keep going. We'll let them work their own energy out, right? Well, here we've got molecules. We have to figure out a way to take the energy away from them. So to slow them down requires removing energy. But adding a solute, or the ions, it causes this solute-solvent attraction, which increases or causes more motion. So as before we had to take some energy out, now we've got to take more energy out when they're mixed together. And we accomplish that by lowering the temperature even more than we did before. How do we compute how much more we need to take out? And that's where the formula in your book, equation 10.2, comes in. It's that delta T equals negative I times, I'll use a really small x, okay? Negative I times K sub F times M. Let's go through and make sure we understand all of the variables in here. Delta T. Now, first of all, what's delta mean? Change in. Delta is a Greek symbol which means change in or change of. When you go rise over run in math, you know your slope for y equals mx plus b, for example, a linear equation. The slope is your rise over run, which is delta y over delta x, x plus b, right? Your change in y over change, your change in your rise over your run, your change in y over your change in x. So it's the change in. Delta is your change. The change in temperature is equal to negative I times K sub F times M. What's the freezing point of my new solution? Water freezes at a certain point. I add a solute to it. What's the new freezing point? The new freezing point is going to be different than the original freezing point. Okay? In water, we happen to know that it's 0 degrees Celsius. But you could use other solvents as well, and they'll have their own unique freezing point. Using this formula, we can compute what the change in temperature is going to be for the freezing point if we add a solute to that solvent. It's going to be equal to the negative I. Now, from your reading, what does I indicate? Okay, it's when we get to the I, what you need to do is remember the nature of dissolving. And the nature of dissolving is either going to be for a covalent molecule, it dissolves as a whole molecule, right? You take a block of pH3, you dissolve it at the molecular level, you've got individual molecules of pH3 surrounded by water. So every molecule of pH3 becomes one molecule. It stays as one molecule, okay? So in that case, the negative I would be 1. For a covalent solute, your I is 1. Why? Because the solute breaks down into individual molecules, making it 1. Okay, that's your gouge, your hint. Covalent molecules dissolve into individual molecules, which is an I of 1. Now, sodium chloride. Hopefully you agree that it's an ionic compound, an ionic solute. What would be the I for sodium chloride? Sodium chloride, what does it break down into? Individual molecules of sodium chloride? No, it's ionic. It breaks down into individual ions. So one sodium chloride molecule dissolves to become one sodium ion and one chloride ion, so the I would be 2. See that? Sodium chloride is ionic. It breaks down into 2 ions. pH3 is a covalent molecule, and it stays as one molecule. So for covalence, it's always going to be 1. And for ionics, it's going to break down according to its molecular formula, its chemical formula. Which is why you need to be able to, if you're given the molecule in words, you need to be able to compute what the ionic formula is. So this molecule may break down into 3 ions, 4 ions, 5 ions. Aluminum chloride, 5 different ions, right? Al2Cl3. Is that right? AlCl3. Right? Aluminum is a column 3, so AlCl3. So that's going to break down into 4 ions, right? Aluminum chloride. AlCl3. It's going to break down into 4, an aluminum and 3 chlorides. Its I would be 4. So negative 4 is what it's going to be. So the I is based upon how the solute breaks down. This K sub F, it's a constant that's based upon the solvent. So I comes from the solute, how it breaks down. The standard here is this constant is the freezing point constant for the solvent. So if you have a particular solvent, you need to be given from a table. You might be given the specific K sub F for a solvent, or you might say, here's a table, and you need to be able to find on the table where that particular solvent, what its freezing point constant is. Most cases on here, they're going to tell you, hey, the freezing point constant is, like for example, over on example 10.3, page 369, it says the K sub F of water is 1.86 degrees Celsius per molality. That's your K sub F. So they'll give you the K sub F. You plug that in. So again, how does the solute break down into how many pieces? The constant for the given solvent, and then the molality of the solution. When you do the math, just by looking at this, knowing that the molality is going to be a positive, that the constant here is going to be a positive, your I is going to be positive, 1, 2, 3, whatever it is, times a negative 1. That means your delta T is always going to be negative, doesn't it? Your delta T is always going to be negative something. In the case of water, delta T here, we would say that it is 0 degrees Celsius. If I do the math over here and my answer comes out to be negative 4, what is the freezing point of that water? If it normally would freeze at 0, and my delta T is negative 4, what is the freezing point of that water solution, that salt solution? Negative 4 degrees. Because I start with where the normal freezing point would be, and the delta is negative 4. So it would be 4 colder. If I have a solvent, and its normal freezing point is, let's say, 10 degrees Celsius. That's the nature of that solvent. It freezes at 10 degrees Celsius. And I do this math, and I get a delta T of -3. It normally freezes at 10. That given solution will freeze at what temperature? 7.
So would the
10. Pardon?
so would the K sub F be the same as the delta?
No, the K sub F is going to be a constant based upon the solvent. So if you dissolve a solute in water, it's going to be 1.86 degrees Celsius per molality. If you dissolve it in acetone, acetone is going to have its own K sub F. Whatever you dissolve it into, it's going to have its own unique K sub F.
So it's gonna be, that's going to be given.
It has to be given to you. Yeah, there's way too many for you to memorize. The most important thing here is to know how to compute the molality and how to determine how the solute dissolves. If it's covalent, it dissolves as one whole molecule, and I would be 1. If it's ionic, it dissolves into individual ions. How many ions does one molecule produce? Sodium chloride would produce 2. 1 sodium and 1 chloride. So the I would be 2 in that case. Do the math over here, compute your delta T. It's going to be a negative number because it starts with a negative I, whatever I is. So your delta T is going to be negative. What does that mean? The freezing point of that solution is going to be lower than what the solvent would normally freeze at. If the solvent normally freezes at 10 degrees and your delta T is -3, it now freezes at 7 degrees. Okay? That's all this is saying. The number of ions, the constant you'll be given, you compute the molality, do the math. It'll be a negative number, which means you subtract that from the normal freezing point of the solvent, and that's what that solution will now freeze at. Let's look at example 10.3 to kind of beat this thing home. It says that 15 grams of sodium chloride are added to 100 grams of water. What's the change in the freezing point for that solution, right? What's the change in the freezing point? Let's just walk through the book answer and make sure we follow the logic. Okay, so 15 grams of sodium chloride is added. We need to know how many moles because we have to compute molality, which gives us the number of moles, right? So 15 grams of sodium chloride with a molar mass of 58.5. So we divide 15 by 58.5, we get 0.256 moles of sodium chloride. 15 grams is the same as 0.256 moles. Now that 0.256 moles is in 100 grams. So 0.256 divided by 100 grams, which is the same as 0.1 kilograms, right? The units have to be kilograms, so they give us grams. So you can see that on the top of page 370. You divide the number of moles by the number of kilograms, and that gives you a molality of 2.56. Molality of 2.56. The next part, they go through and say sodium chloride, when it dissolves, what does it dissolve into? You see where it says NaCl solid, becomes Na positive aqueous and chloride negative aqueous. So when it's in water, the solid sodium chloride becomes 2 ions, sodium ion and chloride ion. That makes the I a 2. When we look at delta T equals negative I times K sub F times M, we've already said that it's -2 because it breaks up into 2, times 1.86, which you were given as the constant for water, times the molality of 2.56. And the answer here comes out to be, when you do the math, negative 9.52 degrees Celsius. Now, the normal freezing point of water is 0 degrees Celsius. With no solute in it, it's 0 degrees Celsius. So this particular solution will freeze at what temperature? Negative 9.52 degrees. If the freezing point of water happened to be, which it's not, but if it happened to be 10 degrees Celsius, when would this freeze? 0.38? Yeah, 0.48. So it would freeze at 0.48 degrees Celsius if the freezing point were 10, but it's not, it's 0. So it makes it easy, right? If it freezes at 9.52 degrees lower than normal, and normal is 0, it's negative 9.52 degrees. The second one there, and the third one. That's why your notes were so short for today. You've got like 3 pages of example problem, right? What's the freezing point of a solution that's made by mixing 2.5 grams of aluminum nitrate in 150 grams of water? Now, what's going to be the hardest part about this? Well, 2 hard parts, right? You've got a mass of aluminum nitrate that you've got to figure out now the molar mass of Al NO3 sub 3. So you have NO3, 3 of those, plus an aluminum. But you're also going to have to figure out what kind of a solute is this? Aluminum nitrate? It's ionic, right? It's going to dissolve into 3 nitrate ions and 1 aluminum. So what is the I going to be? 4. Right? It dissolves into 3 nitrate ions and 1 aluminum ion, so my I is going to be 4. You can see, computing the moles, 2.5 grams divided by 213 grams per mole. That means we have 0.012 moles of aluminum nitrate. 150 grams is the same as 0.1500 kilograms of water. And the molality then is right there, computed on the bottom of page 370. Then, noting that aluminum nitrate dissolves into 3 different ions, 3 nitrates and an aluminum, we know that the I is now 4. And it's in water, so it's 1.86 degrees Celsius per molality. So it's -4 times 1.86 times the molality, which we computed as 0.080. Doing that math, we get a change of temperature of -0.6 degrees. The solvent is water, which normally freezes at 0 degrees Celsius with no solute in it. The delta T is -0.6. Meaning that the new freezing point of the solution is -0.6 degrees Celsius. And one more on page 371. And here the deal is that you're dissolving sugar, and sugar is a covalent molecule. Knowing that it's a covalent molecule, what will the I be in the formula? It has to be 1. Because it dissolves into a full single molecule. So the steps are the same. Taking the mass, dividing by the molar mass to get the number of moles. Putting the solvent, 950 grams, as 0.950 kilograms. Computing the molality, 1.86 as your constant for water, a -1 because it's covalent, gives me a delta T of -0.58 degrees Celsius. Since it's water, it starts at 0. It's 0.58 less than that, so the freezing point is now -0.58 degrees Celsius. On page 372, they want to make sure that you understand that in some texts and some other books, maybe some videos you watch, they will talk about the melting point instead of the freezing point. They just want you to make sure that you understand that that's the same thing. The point at which something melts is the same point at which something freezes. It just depends on what direction you're going. If you're a solid moving to liquid, that place where the solid becomes a liquid is the melting point. If you're a liquid becoming a solid, that point at which it happens is the freezing point, but they're the same point. Depends upon the direction you're moving. So if you're an ice cube becoming water, it's the melting point. If you're water becoming an ice cube, it's the freezing point. It's perspective on which way you're going, but it's the same point. Which is why if we say that the freezing point of a solution is -2 degrees, that's also the melting point of the solution. If we brine the roads and we say the road's not going to freeze until 28 degrees, but it happens to be 26 degrees, what happens? The road freezes. But when is it going to melt? When it gets up to 28 degrees. It doesn't have to wait to 30 degrees or 32 degrees. It comes up to 30 or 28, you know. So the melting point and the freezing point are the same point. It's just perspective on which way you're moving, whether you're freezing or whether you're melting. On your own, 10.7 and 10.8 are there. Answers are in the book. I'd encourage you to go through and do those. Make sure you understand the concepts. Again, I'm not spending a lot of time on how to do this math. It's just simple multiplication. As long as you know what variables go in there, what the numbers would be, then just do the math. And it's straight multiplication. There's nothing, particularly hard. Don't forget the negative. Remember that when you have a solute in a solvent, it lowers the freezing point. It has to go colder before it freezes. Now, when we do boiling point is the same idea, except rather than it boiling at a certain temperature, it boils at a higher temperature. So when we add salt to water, that water is going to freeze not at 0 degrees Celsius, but at a lower temperature. And it's not going to boil at 100. It's going to boil at a higher temperature. We'll talk about that next time, or actually in 2 days. Tomorrow, review questions and practice problems and a quiz. Yes, sir?
On pin 7, what does it mean that says, where'd it go? It says that this molecule is slightly polar.
Slightly polar.
What does that mean?
That means that it'll dissolve in a polar. Likes dissolve likes. They just want you to know that it will dissolve in water. Great. Because if it was nonpolar, we put it in water, they're opposites and they don't dissolve well. Right. That would tend then, if they didn't dissolve, that would probably rise to the top or sink to the bottom, one or the other. But since it's slightly polar, it'll mix and dissolve. You notice on the on your owns, they give you a K sub F. On the top one, the solvent is water, so they give you 1.86 degrees Celsius per molality. On 10.8, the solvent is acetic acid, and so your K sub F there for acetic acid is 3.90 degrees Celsius per molality. So. Notice too, real quickly, that 1.86 for water, degrees Celsius per molality, that's a derived unit, right? It's a derived unit. Why does it have to be that way? The I is always going to be a number, an integer. Just 1, 2, 3, 4, 5, whatever. What are the units? There aren't any. Okay? So it has to work out so that the units left over are degrees of temperature, which is why it's degrees Celsius per molality, so it cancels out the molality.